The mystery of dark oxygen, beneath the breathable sky. Long before the first leaf unfurled toward the sun, before the skies turned blue with oxygen, Earth's surface was a murky soup. Volcanoes spewed gases into the air, an ocean simmered with chemical reactions. There was no oxygen, no ozone layer, no life as we know it. Yet, somewhere in the shadows, deep in cracks in rocks, in the abyssal plains of the sea, and beneath thick layers of sediment, life quietly began to emerge. This life wasn't breathing the oxygen we take for granted today. It didn't photosynthesize. It didn't bask in sunlight. It existed in the dark. And now, billions of years later, that ancient world still exists. It hasn't gone away. It's under our feet, under our oceans, inside caves and crusts of basalt. And in that world, a new mystery has begun to stir: oxygen in the dark. How can oxygen, a gas so strongly associated with photosynthesis and sunlight, be present and persist in places utterly devoid of light? This is the mystery of dark oxygen. Life where it shouldn't be. In the early 2000s, geologists and microbiologists began drilling deep into Earth's crust, looking for signs of microbial life. What they found was astonishing. Entire ecosystems of bacteria and archaea, thriving kilometers below the surface in isolated aquifers and rock pores, were metabolizing, growing, and evolving. This deep biosphere, estimated to contain over 70% of Earth's microbial biomass, is largely independent of the surface world. It exists in hot rock, cold sediment, ancient seawater, and buried organic matter. But many of the microbial species they discovered required something surprising: oxygen. This didn't make sense. These zones had been sealed off from the atmosphere for millions, even billions, of years. There was no sunlight, no photosynthesis, no contact with the breathable air above. And yet, oxygen was there. The first clues: oxygen in ancient waters. In 2013, a study in Nature described deep groundwater reservoirs in Canadian mines that had been isolated for over 1 billion years. When scientists analyzed the chemistry of these waters, they expected to find methane, hydrogen, sulfur, typical signatures of anaerobic life. What they didn't expect to find was oxygen, present in small but significant concentrations. More remarkably, this oxygen wasn't a contaminant. Isotope analysis showed that it had a different signature than surface oxygen. It was older. It had been there for a very long time. Where did it come from? Radiolysis, oxygen from rocks. One of the leading explanations for dark oxygen is a process called radiolysis, the splitting of water molecules by radiation. Deep in the earth, naturally occurring radioactive elements like uranium, thorium, and potassium-40 constantly decay. This decay releases energy in the form of alpha, beta, and gamma radiation. When this radiation strikes water molecules trapped in rock pores, it splits them into hydrogen, H, and oxygen, O. This process is slow, agonizingly slow, but it's relentless. Over millions of years, it adds up. And in the sealed cracks and voids of Earth's crust, the oxygen produced can accumulate, creating a microenvironment capable of supporting aerobic microbes. These radiolytic ecosystems may be some of the oldest and most stable on Earth, with no need for sunlight at all. They're powered entirely by Earth's radioactive core. In this way, the Earth itself becomes a kind of inverted sun, radiating energy from within rather than shining light from above. Microbial alchemy, making oxygen without light. Radiolysis isn't the only game in town. Some microbes have evolved astonishing metabolic tricks that let them produce oxygen themselves, from non-traditional sources. Perchlorate and chlorate respiration. In certain environments, bacteria can use chlorate, ClO, or perchlorate, ClO, as electron acceptors. As they reduce these molecules, one of the byproducts is molecular oxygen, O. This process, called dismutation, allows the bacteria to make oxygen in the absence of sunlight. The oxygen isn't waste, it can be used by the same cell or nearby cells for aerobic respiration. These microbes have been found in deep sediments, hypersaline lakes, and space analog environments like the Atacama Desert. Some researchers believe that this form of respiration could be viable on Mars, where perchlorates are abundant in the soil. Nitric oxide dismutation. Another rare microbial process involves nitric oxide, NO, a reactive nitrogen compound. Certain bacteria can catalyze the reaction, NON plus O. This reaction releases molecular nitrogen, N, and oxygen, O. It's an unusual pathway, but it's been confirmed in some denitrifying bacteria, organisms that live in low oxygen environments but still need a burst of oxygen to perform specific reactions. The oxygen produced is often used to degrade pollutants or to power bursts of metabolic activity. In extreme environments like mud volcanoes or anaerobic aquifers, this mechanism could provide a temporary oxygen boost in an otherwise anoxic world, a living tapestry in darkness. With these new discoveries, the deep biosphere has gone from curiosity to revolution. We now understand that oxygen is not solely the domain of photosynthesis. It can arise from geology, from microbial alchemy, from chemical persistence. In deep gold mines in South Africa, bacteria live 3 kilometers underground, feeding on hydrogen and sulfate, surviving in salty water that hasn't seen the surface for 2.5 billion years. In the sediments beneath the Pacific Ocean, microbial life moves at a snail's pace, dividing only once every 1,000 years, but it persists, fueled by dark oxygen and chemical energy. In underground aquifers, microbes consume methane and release carbon dioxide, playing a silent but significant role in Earth's climate. These organisms live in a time capsule, untouched by surface extinction events, climate changes, or even the rise of oxygenic photosynthesis. They are the ancient ones, the custodians of primordial life. Implications for extraterrestrial life. If oxygen can be created in the dark, sustained over geological timescales, and used by life in isolation, then the possibility of life beyond Earth becomes much more realistic. Europa, Enceladus, Mars, and beyond. Europa and Enceladus, the icy moons of Jupiter and Saturn, have subsurface oceans. Radiation from space could split water molecules at the surface, creating oxygen that sinks into the ocean. Mars contains perchlorates in its soil. Microbes similar to those on Earth could use these to produce oxygen in the dark Martian underground. Titan, with its methane lakes and subsurface potential, might host methane-breathing or perchlorate-respiring life. In each of these environments, sunlight is absent or minimal, yet the ingredients for dark oxygen exist. And where there is oxygen, even in trace amounts, there may be aerobic life. The paradox of the oxygen signature. Traditionally, the presence of oxygen in a planet's atmosphere has been considered a biosignature, evidence of life. But what if oxygen can be made abiotically, through radiolysis or photolysis, without life? Conversely, what if oxygen is being consumed by life in subsurface ecosystems, leaving no atmospheric trace? The mystery of dark oxygen challenges our entire framework for detecting life on exoplanets. It teaches us that life and oxygen may not always go hand in hand, or that oxygen may be present in unexpected places, without the biological markers we'd expect. To find life, we may need to look deeper, literally and metaphorically.
Thanks for watching, and subscribe for the more video.